Hi, my name is Samay Patel. This is my Physics 2211 Lab 5, Choose Your Own Adventure. So the goals of this report are to analyze and abstract data from an oscillating slinky from rest and use the program tracker to create an experimental model of the data, create a theoretical model using GlowScript which takes into account changes in energy while applying the energy principle, and compare and contrast the two models that have been created for this situation. So some of the background information to understand about this topic is to understand the concepts for this lab, there must be an understanding of Newton's second law as well as an understanding of the forces of gravity and drag. To understand Newton's second law, we must understand that for a velocity to change, there must be a net force acting from the object. And for the force of drag, we have to understand that opposite in the direction opposite of the opposite of velocity, and that it typically tends to impede the force acting on the object. From the video that was recorded, the purpose of our experiment was to see how the slinky would react to the force of gravity while maintaining a force of tension. As you can see, there is the position update formula here and the velocity update formula here, along with the force of gravity, the force of drag, and then the force of the spring. So this was the file that was abstracted from Tracker, and this was the data that was presented after. I'll be playing this on 2x speed because the video is a little bit long. That was how the slinky was tracked using Tracker and how the model was constructed using that data. From this, we can take the experimental data off to the side. As you can see, I started by recording only the bottom of the slinky, as that's where its center mass was supposed to be, and that is where, this is where it was recorded at first. But then as soon as the top of the slinky hit the bottom, that is when it started falling in a linear path. So the GlowScript code that I created, this was the mass that was provided from the video. This was the initial position that was abstracted from Tracker. This was the velocity vector. You see there's no velocity initially. The time is at 0, the delta t. This is the frame interval rate. This is the gravity vector. This is the j hat vector. And this is the force of drag that we predicted it. So continue. This was for the first 5.583 seconds, which is where the two slinkies are going towards each other. As you can see, in this case, the force of gravity is this way, but this is F. In this case, would be the force of tension, which acts to eliminate the force of gravity. In this case, acting as a perfect model to each other. And in this case, this is just how the velocity was updated, the position was updated, and obviously how the curve was plotted. Continued on from time second 5.583 to 8.533. This is when the slinky is falling towards the ground in a free fall motion. This case, this is the force of drag that is associated with the data. This is the force of gravity that's associated with the data, and this is how it impedes on the force of gravity in this case. And obviously, the slinky velocity and position update formula, and obviously, this is the same concepts as before. So comparing and contrasting the models, they look relatively similar. Obviously, there are some slight discrepancies in between each other because obviously one has an experimental model and one has a theoretical model. And in this case, the experimental model might have different, conditions and all that, as opposed to what would just be expected from a theoretical model. So conclusions about the lab. In the first part of the evaluation calculation loop, the bottom of the spring does not move to the equivalent of the force at that point. At the point, the force of gravity and tension are equal, as I said before. The second part of the calculation of the forces are not equal, and therefore leads to a net force on the object and helps it fall downwards. When there's a net force acting on the object, obviously there's a change in velocity as well. This helps demonstrate the concept of Newton's second law, which is the purpose of what we're trying to understand about this experiment. If there's a net force, then there can be assumed to be a change in velocity. If there's no net force, then there's no change in velocity, and the object is in an equilibrium state. And some errors that might have occurred in the lab, as in any lab, there are any errors. One of these errors is that due to the experiment being performed in an outdoor setting for the experimental model, external forces might have had a play on the molecule. Along with this, we cannot account for all the tiny discrepancies in the spring, obviously slight changes in air resistance or gravity that might have occurred. And the last error is that the analysis of the center of the mass, while in this case we assume that the center of mass is at the bottom, we don't know for sure how this would occur. And we might know that in a different setting it might be throughout the spring or just not in that one concentrated area. Thank you.